Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream.
I think we're here. We made it.
Yes, we're here.
The two of us are in the same room together.
Yes.
It's been
a few weeks.
10 years.
10 years.
No,
I was going to say a few weeks.
I might have overestimated. but welcome everybody.
Yes, welcome, and another episode of Ask Us Anything about electrochemistry. You've heard all the boilerplate information. Last week we streamed to LinkedIn, YouTube, and Twitter.
You did it 2 weeks ago, and last week I think was my first week doing it.
All
by myself, and I think I did it correctly, but it's possible. No, I think it worked.
Yeah.
Technology is a thing. So,
it is definitely definitely a thing.
I think we are doing that now as well. We are on both Twitter and LinkedIn and YouTube and in the internet tubes and everything. So,
and if there are other platforms that you're on that aren't these, and you think it'd be cool if we stream to those other ones, let us know. Maybe we'll do that.
That's right. We're not satisfied until we are streaming to every single corner of the internet.
Everywhere electrochemists can be found.
That's right.
We will find them.
every lab bench that you are hiding under, we will find you and stream directly to your computer or phone or something, I guess. I don't know. Well, anyway, good. It's a pleasure to be with you. And Alex and I are finally back together. We got the band back together. We're very excited.
Yeah, that's right.
And in the spirit of cooperation or answering questions, we will get to it because we have a few folks have asked questions. I guess Yaswant had asked a question just like 10, 20 minutes ago. We will get to you. Yeah. We also have a couple, I think there's a couple loaded up from, again, I don't remember, was it comments on our YouTube channel?
We had one that was a comment on our YouTube channel.
This one I think was also from our YouTube channel that I added. Okay. It might have been even like late last week. So, just actually, now that I'm looking at it, I'm seeing that I put the at Wilson something and Made something as well. I apologize again for the names that we can't pronounce. Alex already apologized for that in the preview, so I won't. Anyway, but both of these users had asked a similar, I guess, I sort of aggregated their questions together, and it was how to run chronocoulometry, but specifically the question was more about calculating the effective surface area of an electrode. And so we've done this, so I've done this a few times, I think, over the, year or so that we've been doing these. But what I wanted to do was show how to calculate the electrochemically active surface area, for instance, live with you. I'm just going to do this procedure. Let me share our software because I have some data that I can show. Make sure that it's working, Alex, that they've got. And you can move us wherever needed. If you want to do I don't know, whatever the method that.
Yeah, I'll move us if we get in the way.
Okay, perfect. So I'm actually not going to talk too much about chronocoulometry, just sort of in the interest of time. I know that there's probably a few people here asking questions. I don't want to take too long. But in short, the answer for chronocoulometry is kind of buried in this explanation too. Chronocoulometry is just kind of another name for chronoamperometry, where you're calculating the charge. Coulometry, right? Think about the name chrono's time. Coulometry is aggregate charge, coulombs, right? So how the amount of charge over time. And so when you're passing, setting a potential usually and getting a certain amount of current, you integrate that current over time, you get the amount of coulombs at any particular moment in time. So that's just kind of what's meant by chronocoulometry. It's kind of an analysis of chronoamperometry. And so as that relates to this, hopefully you'll see why I'm kind of combining those two into one, if you will. And so the ECSA, one of the trickiest things about the electrochemically active surface area in general is that for like any particular non-specific reaction, it can be difficult. The most commonly understood method involves this particular type of CV, which many of you might recognize. This is like, I don't know, remember how I got this. You can see it's platinum and half molar sulfuric acid. I have had these data for quite some time. I don't, it's old in any case. This is the sort of standard bearer, if you will, for calculating electrochemically active surface area, right? And the reason is that we know the specific, I guess, amount of charge of part of this curve, and that lends itself very nicely to the ECSA. So I'm going to show you how to do this, right? There's two methods or two ways you can do this. One is by using the CV data itself. More conveniently would be using the current versus time plot of your CV. So this is like, you can see this is the voltammogram. I took one, cycle. So this, for example, was done a CV. I don't even know how many times, maybe 5 or 10 CVs back and forth, something like that. Let's say 20 segments. So this was like 10 CVs. This voltammogram is just probably my favorite one, whatever. The current versus time, you can see this is where it goes scan positive, scan negative, scan positive, negative. So if I just sort of select a segment at random here, let's just say this is the one that I want. I'm going to kind of zoom in on this segment. So this is like 1/2 of the CV. Okay. What we're going to do to start our ECSA is we're going to recognize, let me back up and come to this here. What we're focusing on is this region right here. Okay. So the region close to 0, basically, now this is shifted because of the reference electrode used, but the most negative region, if you will, is the platinum hydrogen adsorption desorption region. Also, as you go further negative, it's the hydrogen evolution reaction or the hydrogen oxidation reaction, depending on which direction you're going. But basically, this part of the curve is where you're adsorbing and then desorbing hydrogen on platinum. And that has a well-established and well-known specific Coulomb charge value of 210 microcoulombs per centimeter squared. That's the number. So I have the papers. I can sort of pull them up in a bit, but I want to show you the calculation. That's kind of mainly what I think this question was. They wanted to see how this is done physically. And over many, many years, researchers have settled on this number. It's like the sort of accepted value. So what we're going to do is subtract basically this region right here in the middle. This is the only part of the platinum curve in acid where you have effectively just double layer, this thin region right here. So what we do is we sort of subtract this thin region. You can think about like, I'm trying to draw a rectangle without selecting. Don't select. Okay. So we're going to try to subtract this little band from our calculation. And we want the area under the curve that is associated with just the hydrogen adsorption and desorption. So the upper part or the bottom part, it doesn't matter which. We can do one or the other. Sometimes you do both and you sort of compare them. So what I'm going to do is I'm just going to add an area tool. I'm going to do one at a time. I want to get this bottom point up here a little. Let's sort of zoom back in, get this over here. And so basically I want this region here. You can see where I'm zooming in. I'm just going to eyeball this for now. If you were doing this with your research, you might be a little more precise. I'm just going to kind of do this quickly for you here. So this is like 62 microcoulombs, right? What I might do as well is do one on the negative portion as well. So let me select the segment, select the bottom portion. Sometimes, again, this is what people will do. They'll take the average of it, or they'll just take one or the other. Let's get the area tool for this. Let's hone in on just the bottom part. Kind of move this around. And you can see, they're roughly the same number. It depends on exactly where I pick my limits to be. Sometimes you take the ratio of these and say that's some sort of efficiency, something of that nature. The bottom one here, this is the platinum adsorption. The positive one is the platinum desorption. So let's just sort of split the difference here and say 64. I don't know. It doesn't even matter, really, the exact number in this example here, but 64 microcoulombs, right? I'm going to stop sharing. I'm going to share PowerPoint so I can just do the calculation with you. here. And so this is literally how you do the calculation and how you get your electrochemically active surface area. So let's just say I had 64 microcoulombs associated with the platinum. That's supposed to be a P because letters are hard to write. A platinum hydrogen, basically like adsorption. I don't know how this is necessarily always written. Adsorption, desorption sort of process. That's just what it is. This has a theoretical value of 210 microcoulombs per centimeter. Again, if there are follow-up questions, I won't do it now for interest of time. If there are follow-up questions, we can monitor the chat. I'll show you where this comes from. I believe I have the papers saved on my computer here where these come from, and I can explain where they come from and why. For now, you'll just have to believe me that this is the number. Okay, 210. And so all we're literally doing is taking 64 microcoulombs divided by 210 microcoulombs per centimeter squared, right? And so microcoulombs cancel, centimeter squared goes into the numerator. And so this is some number. Let's see. 64 over 210. It's 0.305. Okay. Equals 0.305 centimeters squared ECSA. Now this probably, I don't actually remember. It's been literally, I don't know, 9 years since I got this data, but this is probably performed on one of our common disc electrodes. Like my company makes these disc electrodes, and they have a geometric surface area of 0.196 centimeters squared. So this is like, just say geometric surface area. And so the sort of analysis that you're doing here when you're getting your ECSA is by saying, okay, well, I don't know, sometimes people will do like a ratio, like you divide like 0.305, so it's like 1.7 is some factor, like roughness, maybe it's like roughness, or it's like active groups make the ECSA higher than the geometric area because you've made a film of platinum on carbon that's really good. Or, so there's a lot of subsequent kinds of analyses that folks will do to explain why the ECSA is some number that's higher, or maybe it's lower because your material isn't particularly active, et cetera, right? But that is, in short, how you calculate ECSA for this specific kind of process. Now, again, one of the hard things about this is, let's say, for instance, I'm studying a different nickel in alkaline media and methanol oxidation. Okay, well, what's the specific, coulombs per centimeter squared for that? That may not be tabulated, or you'll have to find it. Like this one that I showed you is like the most commonly done, most well-known, ubiquitous one, which is why sometimes to get ECSA, people will test their material against that. If it's a platinum-based one, right? They might even be testing it not for hydrogen adsorption, desorption. They might be testing platinum for some other process, but they'll calculate the ECSA using that experimental method. So they get the ECSA, because we don't always, as far as I'm aware, I don't know many other like microcoulombs per centimeter squared numbers that are out there. There might be some. You might have to like scour the literature to find them. But it's not clear, I suppose, exactly how to get ECSA for other methods. But I wanted to show you that one because that is probably the most commonly done in the electrochemistry world, right? To calculate ECSA, that's like the method for the most part.
Very good. There was a question that came in from YouTube. Question is how to determine the frequency range for electrochemical impedance spectroscopy. What are the factors that are needed to be considered to obtain a meaningful result? I think most people, for most systems, will start with 1 megahertz on the fast frequency, and they'll go to 1 hertz or maybe 100 millihertz or 100 millihertz or something. I think it depends on your system, generally speaking. We usually start at 1 megahertz for most systems, but a lot of the very fast frequency data isn't that useful. It's mostly in like 100 or 50 kilohertz range, where you actually like, okay, the useful chemistry or useful chemical information is kind of contained there. And then usually you'll get some at least more complete semicircles if you go to the very, very low frequency. And maybe you'll get like maybe a few extra data points, but it always takes a lot longer. And there's questionability with how stable the system is as you go to those lower and lower frequencies, because they do take a long time. They're, as you know, everything I know about impedance comes from you. So I'm just so it's like, oh, I don't know if I'm missing any other things.
I mean, I mean, what I would say as a advice, if you will, is it just exactly what Alex said, is that like, if you're sort of what frequency range should I use? 1 megahertz to 0.1, like 6 points per decade. Mm-hmm. Like if you're not sure, for example, the beauty of impedance as a tech, like I would say like an exploratory technique, is that it's non-invasive, right? Mm-hmm. So if you're trying to figure out what frequency range is most appropriate, you will most probably not do any damage by doing too wide a frequency range, right? The same is not true of cyclic voltammetry, for instance, or bulk electrolysis. Like if you're just sort of trying to figure out your potential window for cyclic voltammetry and you're like, well, let's just put plus or minus 10 volts. What's going to happen? Yeah, well, you're going to destroy your electrodes. What's going to happen, right?
Yeah.
Right. If you put in a megahertz and you go to a microhertz, the only thing that's wrong is that it will take forever, right? Yeah. Or that you'll get really gross, unstable, just nonsensical data at really high frequencies, but you're not going to damage anything unless your parameters are really out of whack, your amplitude's too high, whatever. Okay. Yeah. But for the most part, the worst that will happen is your data will be ugly, but your sample, your system, your electrode will be undamaged. So it's a good technique from that perspective, that you can discover the appropriate frequency range without much worry about the integrity of your system and your electrodes.
Mm-hmm. Yeah. And then of course, we don't know what system you're studying, so right. You'll have to play around with it. There may be more information in the high frequency range than the low frequency, but yeah, that's it. And so if you have any follow-ups, please let us know. All right, so moving on. People can still ask us questions. Which one do you want to?
I was thinking you might do the current decay one. I think this was asked on your chronoamp video.
So I had a comment on a YouTube video that I made on chronoamperometry, and the person's asking, so the current decays because there is less species to oxidize, and this is specifically not so much a question, but perhaps more of a clarification to make sure that they understand what's happening. And so in that video, I'll just kind of describe. I was speaking or talking more about the. Let's see.
Let me make sure everything is good.
Everything is good.
Yeah, we're good.
Okay. I was just describing that in a chronoamperogram. So you have time, you have current. You initially, this is where the experiment kind of starts. This is like your T0. And then you see a spike in the current, and it's followed by a gradual like decay over time. So the decay is, and I was describing this within the context of a 3 electrode system where that's all solution based, and the math that describes this kind of shape is the Cottrell equation. So let me see if I can find Cottrell. Yeah. So this is the Cottrell equation. It states that the current is equal to NFAD, the diffusion coefficient, to the 1/2 times the concentration, all divided by the square root of pi times the square root of time. And I'll just hide this so we can see all the parameters. So this equation kind of shows or demonstrates this type of shape. But fundamentally, what is happening, why do we get a decay? And the decay has to do completely with diffusion, specifically with the fact that if you have an electrode here, and let me just kind of, let's say this is your electrode, and you have some, molecules near the surface. Only the molecules that are at the electrode surface, like right here, are going to actually undergo an electron transfer process. So it takes time for some of these molecules to react with the surface. And as time goes on, instead of having, these black molecules, we now have more of these blue molecules, right? We have blue ones here instead of black. They've been oxidized. So now it takes longer because for me to actually oxidize what's happening, I need to wait for a molecule here to diffuse towards this electrode surface, and it takes longer, right? And that's why the current decays, because the current represents a rate. It represents how many molecules per unit time are undergoing this oxidation reduction process. And specifically, as the diffusion layer thickness increases, as we have more and more of the oxidized species form, we have to wait for molecules further out in the bulk solution to make its way towards the electrode surface. Another kind of visualization of this, if we will, is so let me actually just share this 1 second. Another way that we can kind of think about or visualize this is we can actually simulate, and I think I simulated this process, but it happens very quickly. But let's say we are doing an oxidation reaction, and then we're doing bulk electrolysis. Wrong button. So we do oxidation, and set this potential, and then we're going to step to 500. Then when we simulate it, we get this, which is not very interesting per se. But I think and I'll make this a little bit longer. Let's make this like 20 seconds or so. So if I were to kind of simulate this process, that's the surface concentration. But the concentration profile here, as a function of distance, this is the diffusion layer thickness increasing over time. What happens, and let me stop this and then reset, is that at the beginning, I just have the blue, technically, is my oxidized species, and the red is my reduced species. So in the bulk, there's lots and lots of my red species. But then as I start the experiment, there's going to be a lot of blue that starts to exist near the electrode surface. So this is the diffusion layer thickness increasing over time. And I need red, or this red molecule, or A, to react with the surface. But it just takes a long time because this is where all the molecules are at. They're all the way here. And they slowly have to make their way to the electrode surface. I have so little of them at this point near the electrode surface. So that's the diffusion layer thickness increasing over time, at least a visualization of it. And that describes why your current, as you can see, our current really decays actually quite rapidly on the time axis. But that's why we get a decay. So hopefully that is I answered that question via text to the person writing it. But if they are interested in actually learning a little bit more about why the current decays while oxidation occurs, hopefully that's helpful.
Very nice. Always good to show simulation.
Yes.
I like that we have simulation.
We do have simulation. And you can have it too if you want. You can
Aftermath Live.
Yes. And you can simulate chronoamperograms and cyclic voltammograms and learn about mechanisms and things like that. So we encourage you to give it a shot.
Indeed. So this question from Yaswant has was just even before we sort of went live here. So it's, I guess, chronologically first. So Avengers, I see your question. We'll get to that in just a second.
Yeah.
So Yaswanth asked, I mean, it's kind of a general question, so I'll just talk briefly about him, but it's actually probably something that requires a lot more explanation or even study, I suppose. But can you explain about OER, ORR, HER, HOR, and overpotential along with baseline correction? So nothing too much here. You know, that's just all the things. I'll try to explain a little bit about these, but again, as I'm being a little tongue in cheek here, this is quite a lot of things to cover in I guess, a short amount of time, but I'll do my best. So I'll define each of these and write the equations and then try to talk a little bit about it. What was it? Baseline correction. So before I even forget here, right? Overpotential and baseline correction. Okay. So ORR is the oxygen reduction reaction. So that is oxygen plus 4 electrons plus, I'm drawing it for acid. I'm just not going to show the alkaline one. There's different reactions depending on whether it's acid or base. I'm just assuming acid here. Okay. Oxygen, it's a 4 electron process with 4 protons. You can see there's 4 H's and 2 O's. So this gives me 2 waters. 2 H, 2 O. Okay. That's the oxygen reduction reaction. This has an E0 of 1.23 volts versus RHE or NHE, whatever. They're all the same. SHE, QHE, PHE, JHE. I don't know. Take your pick, right? Okay. The oxygen evolution reaction is quite literally just the opposite direction of the oxygen reduction reaction. I'll draw it sort of for completion here, but it's a little redundant, I suppose. But basically 2 waters gives you oxygen plus 4 electrons plus 4 protons. So the oxygen evolution reaction and the oxygen reduction reaction are quite literally going one direction or the other, effectively. And they have the same E0, right? Of course, because the E0 is sort of defined for the reduction. And so as it relates to overpotential, when we talk about the overpotential, I don't know if the question is blocking the bottom part of the screen. If you need to,
I can hide just a minute.
Yeah,
you're good.
Okay,
yeah,
perfect. So overpotential is equal to E minus E0. Okay. And so what we talk about with an overpotential will depend basically on what we're studying here. And so graphically, very broadly here, I'll just try to, I don't know, illustrate this if I can. So if what we have here is this is voltage and current, and if this is 1.23 volts versus NHE, effectively, if I'm doing ORR, okay, and this is 0 current, what we're looking for, I'll just sort of draw the intersection between these 2 points. So this is 1.23 volts and this is 0 current. What we're looking for is some catalyst that's going to, like, as it sweeps negatively, it's going to start to decrease in current, go negative current, which is a reduction reaction. And so this is the ORR. Now, with the overpotential, you might have catalyst 1 that does that, catalyst 2 that does this, you know, catalyst 3 that, like, does that. Okay. And so effectively what we're looking for with the overpotential is like this point here, this point here, you know, this point here. It's where does it, like, drop? Where does it start to dip, basically? And so, for example, this blue overpotential looks like it's very, very small. Let's say this is like, you know, 50 millivolts. It's like excellent. It's a great happy face. This is a great catalyst, right? And then the green one, my overpotential, like where it dips down, right? This point right here, whatever. Let's say that is an overpotential of like 200 millivolts. And it's like, okay, it's all right. Maybe it's fair, right? And then the red one you can see that it doesn't start dipping down. It should dip down here, 1.2, like that's where it should happen, right? But it doesn't quite, because the catalyst kind of, it's not that great. Plus the current doesn't drop as steeply. And so this overpotential, is like 500, millivolts. And that's a really bad one. Okay. So this is kind of what we're talking about. When we're talking about overpotential, is that people are looking for when the catalyst starts to perform the reaction of interest in comparison to the standard potential, corrected for the reference electrode, corrected for pH, and all these kinds of things. I know that's a lot. I'm not getting into all of that specifically now. It's kind of a lot to cover, especially since you asked about so many reactions, I suppose. Again, just the other two reactions that you asked about, the hydrogen evolution reaction and hydrogen oxidation reaction, similar situation. They are one direction or the other, or the same reaction. So the hydrogen evolution reaction is basically 2 protons plus, what are my twos like? I can't draw them the same way twice. You know what I mean? Sometimes I do the little loop and sometimes I don't.
Yeah, no, I don't know. I hear you.
I can't. So I feel like when I do a superscript, I just do like a quick one.
Yeah.
And when it's a big one, I want to do the loop, and I don't know why. It's like it's a bit strange.
Yeah.
So if it's a superscript, I just like do that.
Yeah. Now I have to do is just make that just smaller, which is
but it's harder to do a loop when it's small.
I understand.
This is a very important conversation to have. So the standard for this is 0, right? This is, now I'm gonna draw NHE is probably what I should have written before. It's more like the technical whatever.
Normal
anyway,
hydrogen.
Yeah, whatever. RHE, NHE, SHE. They're basically all the same.
That's very similar.
We just sort of assume they're all the same. Anyway, this is the reference like reaction, right? Everything is referenced to hydrogen. So it is by definition 0 volts. And then the hydrogen oxidation reaction is what hydrogen gas goes to 2 protons, 2 electrons. It's just going the other direction. It's the oxidation of the above reaction, right? And so same kind of situation, right? So this is studying oxygen reduction. If I'm studying oxygen evolution, it would just be going in the other direction. So I would have a positive current uptick, and you're seeing where that positive uptick occurs. For hydrogen, for the hydrogen, it's the same thing. It's the same sort of idea. It's just that this instead of 1.23, this would be 0 volts, right? And we're just saying, oh well, how good does my catalyst do it? Where does it happen? Or whatever. It's the same kind of phenomenon, right? And then the idea of baseline subtracting is, I feel like it's just a little more complicated. I don't know exactly how it's like if you have like a really fast scan rate. I'll try to like illustrate this a little. If you have, for instance, like you're doing a CV or something, and you're like looking for, let's say you're looking for the oxygen evolution in this case. So this is 1.23, and you're looking for like where it ticks up for the oxygen evolution reaction. But this right here is current 0, right? Well, this you might say is a baseline. So, you might sort of subtract this from all of these points. So you might like shift the whole curve down so that this right here is like, 100 milliamps or whatever. I'm just making up numbers. But this baseline here, this point right here is 10 milliamps. So you might report, for example, 90. You would subtract the baseline. Something like that. I mean, it depends on your system. It depends on the situation, what you mean by baseline. If it's just like the double layer buildup as you're scanning, if it's like the background current of your substrate or something like that. I don't know exactly what process you're studying or whatever, but sometimes that's what you'll do is you'll subtract the double layer, the impact of the double layer, something of that nature, I guess. So that is hopefully a somewhat quick covering of that question. Again, it kind of had a lot of parts to it, so I wanted to talk through a little bit of it, but it's a little hard to like cover OER, ORR, HER, everything in full detail in under 5 years of a PhD study. So that's the best I can do for you a little quickly, I suppose. Hopefully that kind of gets a baseline answer, I guess. So I know we have other questions we'll try to get to here. So.
Yeah, a few questions coming in.
So, yeah, Avengers had the
Avengers, has a question, which is it's good to know that the Avengers still have electrochemistry questions.
They asked a question last week, and I spent at least 2 minutes talking about how much I miss the Avengers movies.
Yeah, the old Avengers,
the old up through Endgame.
Yeah, yeah.
So
me too. Hopefully, maybe Avengers can do something about that, but maybe not.
It's over. It's just over. It's
over.
Fine.
They had their run.
Can always rewatch. That's all.
You have a lot of movies to rewatch.
Exactly.
So Avengers asks, how does quantum tunneling affect charge transfer kinetics at the electrode electrolyte interface, and what are the implications for nanoelectrode design in high energy and high efficiency energy storage devices? So I'm going to take a stab at this.
I don't know anything about quantum tunneling, but I can answer the second part.
Yeah. So quantum tunneling in general, it occurs in it's the main, tunneling in general is just when an electron or a particle can transfer through an energy barrier that it otherwise could not transfer through under classical mechanics. This happens a lot for scanning tunneling microscopes are all based on electrons tunneling to create a current in an image. Tunneling, generally speaking, my kind of limited thoughts or understanding of it within the context of electrochemistry usually has to do with the difference between homogeneous and heterogeneous electron transfer. So homogeneous electron transfer is kind of the view where the electron transfer from the molecule to the electrode tunnels through the solvent. So whenever we have, and I think I have an image or something like that. Let me actually look for a talk that I think I may have given a while ago. Give me one quick moment. So if I share this, I think I have this. And if it's not, then I'm going to just say, sorry. Is my screen sharing?
Yes.
There we go. All right. So that's not the picture. That's a picture. Did I talk about cyclic voltammetry? I think I talked about cyclic voltammetry. This is the
presentation that you covered quite literally everything.
I covered literally everything.
It's got to be in there somewhere.
Presentation.
Finding it.
It may have been the Villanova one instead. But this picture is still helpful. So I'm just going to blow this up a little bit.
I moved the question so you can show.
Yeah. Oh, thank you. Yeah. So, and I'll just get rid of this for now. So basically, if we think of this as our electrochemical system, and I usually have these kind of orange and red dots that are the redox species. This is the electrode surface. There are instances where the molecule needs to be at the electrode, like chemically bonded to the electrode surface for an electron transfer to occur. In that case, for any electron transfer to occur, we say that there must be sufficient orbital overlap between the molecule, the redox molecule, and the orbitals of the metal atoms of your electrode, such that an electron transfer can occur. Some people believe that, and in this particular case, the redox species and the metal, they kind of form a bond. And that bond, that means that reaction only happens between that particular metal and that molecule. So if it's the case that it doesn't form a strong bond, you won't actually get an electron transfer to occur, or you may have a strong overpotential between that. So this is like the lobe of one orbital of the metal, and this is the lobe of the orbital of the molecule, and there's good interaction. Now, sometimes, let's say I have a molecule here, and there's this solvent molecule, right? That's kind of in between. There is this idea that the electron actually transfers, it tunnels through the solvent molecule to the metal electrode. And that is the case where there's very weak orbital overlap between the molecule and the electrode, but the electron transfer still happens. So in that case, it almost doesn't matter what metal electrode or conductive electrode you have, you're able to get electron transfer. And this is one of the most, I don't know, this is actually one of the first things I did in as a graduate student, was I literally, to test whether or not something was a heterogeneous electron transfer or a homogeneous electron transfer, is I just took different metals, silver and copper and gold and platinum, and then I took that same molecular system and I tried to do the same CV. And sometimes you'll get, if it's homogeneous, you'll get the same cyclic voltammogram, um, like for each system. It's like, okay, this is platinum, this is gold, and then if you have one that's is green or something, this is like copper or whatever, and like all the redox potentials are exactly like in the same spot, plus or minus a little, for error, but they all look the same. But then you may do some electrochemistry where, like, okay, this is your voltammogram on one metal, but then on another metal, it's like it's over here and it's irreversible, or quasi-reversible. And it's like in this situation, you have heterogeneous electron transfer. There's actually electron transfer where these two guys need to be strongly connected to one another, such that the potential for this reaction to occur is based on the energy of these two guys sharing with each other. And sometimes that's a much higher energy than on one metal than on another metal. So that's my kind of limited understanding about the implications of electrode kinetics. And this is absolutely a kinetics issue with regard to tunneling, quantum tunneling. So I hope that was helpful.
So is the message of that then, to the point here, probably with a homogeneous rate going like tunneling through the solvent molecule that's not like doesn't have a requisite requiring the orbitals to line up or whatever, that would be faster kinetics because it just sort of goes straight through. Or not necessarily.
Not necessarily. It just means that the so to a degree, like you could always have like a very high overpotential to get the rate, to be high enough. But like this, I have observed is a big issue with like well, you were just talking about HER and OER. So sometimes like platinum and hydrogen, can form bonds very, very easily, make and break bonds very, very easily. But like hydrogen and silver or hydrogen and gold, that is like much, much higher potential. So you can get the reaction to happen at the same rate, but the overpotential is just way too high. And that's because it's a heterogeneous reaction with platinum and hydrogen than it is platinum and or gold and hydrogen. But conversely, if you were looking at ruthenium hexamine, for example, or ferrocene or ferrocyanide, that electron transfer is all tunneling. You can do it on gold. You can do that reaction on platinum. You can do that reaction on glassy carbon. And it doesn't matter. It happens at the same redox potential at the same rate. Because there is no strong overlap between the metal and that. So
then basically, like at the same potential, the kinetics on one are better than the other.
Yes.
So perhaps in some sense, depending on the potential, the kinetics might be the same. But for the same potential, the kinetics of a homogeneous process are going to be a lot faster.
Yeah.
The same potential, let's just say.
Yeah.
That makes sense. The thing I was going to say, which may not be exactly related to the tunneling phenomenon, but the implications of nanoelectrode design with energy storage devices, it can vary depending on your system. If you're working on fuel cells or you're working on batteries, as far as energy storage devices, I can't speak as much to this process for like solar cells, for instance. But one of the implications of this are that when you go to very small particles, you can sometimes impart electronic conductivity on a material that otherwise does not have any. So one of the implications, in short, is that somewhat or fully insulating or semiconducting materials, if their particle size is small enough, can become conducting, or at the very least, can participate electrochemically with adjacent conductors. So, for example, very small nanoparticles of not super like well conducting materials, but they're so small that when they're immersed in a matrix of like carbon, right, which is very conductive, you can get electron transfer at their surface because the adjacent carbon material, right, whatever it is, imparts electronic conductivity to the non-conducting species. This is the theory anyway, and it's, you know, there's some evidence for this. Of course, there's a lot of different studies of materials, you know, and composites and things of that nature. So that's one of the implications of nano materials. Very, very small materials can have a positive impact on energy storage devices as a catalyst, for instance, because of its electronic properties change when you get that small. Now, there's other cases, for instance, where like in batteries, as you decrease the size and go to nano size particles, in a lot of situations, you dramatically increase the surface area just by virtue of the fact that there's smaller particles, right? Like a bunch of smaller spheres. You know, everything's a perfect sphere as you go to, you know, modeling and whatnot. But right, if you just assume you have a ton of tiny little spheres of particles compared to one large sphere, the surface area is much larger. And in, for example, in batteries, that's counterproductive. So one of the other implications is that nano-sized particles sometimes is a detriment, depending on what it is, and in certain situations, the smaller particles leading to larger surface area can lead to problems with things like secondary storage mechanisms that are counterproductive to the primary storage mechanism, and that's actually a detriment to energy storage devices. So it's a bit of a positive and negative in some ways, I suppose. But I do think that there's still a tremendous amount of research that happens pretty consistently on nanomaterials with energy storage because of the promise of greater surface area for systems where that is important and does help and isn't a detriment. And like I said, for ways to impart electronic conductivity on materials that show promise for in other ways, but suffer from a lack of conductivity, which makes them obviously not good candidates for electrochemistry.
And just to let everybody know, we do see that you have questions on YouTube and on LinkedIn. We are getting to them, but we do want to be thorough with our answers. So we do see you and your questions. And speaking of which, here's the next question from LinkedIn. Mustafa is asking, could you please speak about the effects of numbers of charges of the ions in different types of batteries, like Li plus, zinc 2 plus, or aluminum 3 plus, in terms of diffusion and mobility inside the electrolyte? Do you know anything about diffusion? And I mean,
I think the conventional wisdom is that the bigger the ion, the slower it diffuses, right? Is there something to that? So generally speaking, there's things about, for instance, the size of the ion can be related to its charge, but also it's as you go down the periodic table, the nucleus, how big the nucleus is affects how big it is.
Yes.
And then I'm going to get this wrong. I'm going to try to do it right. So a negatively charged species is bigger than a positively charged species.
Yes.
Because the amount of there's more electrons. So like the cloud, it's bigger. Right? Is that did I do it right? Okay, I didn't do it backwards. When I was drawing my diagram for one of my things with the double layer, I had it exactly backwards. I drew I had K plus and CL minus.
Yeah, and the K plus was
I had the K plus huge, and you're like, that's backwards. I'm like, I did it backwards. yeah, exactly. Because when it's a positive, if everything's drawn more in, because there's not enough electrons.
Yeah.
Basically, right? So everything is sucked in more to the nucleus, which is positively charged.
Yeah.
Something like that.
Yeah, right? Yeah. It's like I was always taught like it just in chemistry, it's like you're pulling, the positive charge is trying to pull the the electron cloud close to it. If there's so many more electrons than positive charge, then the electrons can kind of move outwards more. And if it's lower, if you have a lot more positive charge than negative charge, it's easier to pull those electrons closer in. So yeah, in this case, of course, keeping in mind what row you are in the periodic table, you of course have to look at the size of the ion, because I think
lithium's quite small.
Lithium's quite small.
And Li plus is very small, because it's one of the reasons why it's got tremendous potential in general. It's a small ion. It's element number 3. So it's, it's quite energetically favorable to move an electron to and from lithium. Right. So that's why it's in every one of our phones at the moment. So it's got a good diffusion, relatively speaking, probably compared to aluminum and zinc. Again, but it's twofold, right? So it's everything that we just talked about, which is to say, in theory, the nuclei of zinc, aluminum, and lithium are different sizes, but let's pretend for a moment that they were the same size. That would suggest that Al3+ is smaller, because it's more positively charged. So it's sucking all the electrons more into the middle, right?
Yeah. So take a quick look.
Yeah. So there's that phenomenon of it, but then there's other phenomena. For example, the diffusion and the mobility will also be related to, it has a solvation radius, and the solvation radius in solution, like all of these have Al3+ or Li+, whether it's in water or it's in non-aqueous or whatever. You can imagine water is just the easiest to talk about, right? But if it's in water, Li+ or Zn2+ doesn't exist by itself. It has water molecules around it, basically. Like it's called solvated. That's what it is. So its mobility or diffusional, properties are probably going to be dependent on how big and how much solvated water is around it. And so you have to sort of look up those solvation radii, for example. That's another thing that's tabulated somewhere, right? And then really, frankly, it's like just the diffusion coefficients are tabulated for a lot of these in standard sorts of, solutions or whatever. You can just look up the diffusion coefficients, and in general, what is it, the higher the diffusion coefficient, the faster the molecule diffuses. So mobility is diffusion and mobility is somewhat synonymous, I suppose, but there's things like transference number, and there's stuff. There's a lot of ways there's a lot of ways to think about this through, but in general, right, I think it's probably something like what we just said, which is to say that if it's the smaller it is, the quicker it moves. The analogous kind of experiment that, for example, I did, I think when I was even an undergraduate, was like, we looked at the elution times, which is just how fast stuff moves, but you're looking at it with gas, for instance. So you can measure, and I forget how it worked exactly, but I did an experiment when I was an undergrad about like hydrogen gas, nitrogen gas, argon, oxygen, a few different just typical gases, CO2, how fast they move through like a capillary or something like that, right? And essentially it's just related to how big they are. So hydrogen moves really fast because it's just two,
small.
H2 and H is one, proton, it's like 2 protons big or whatever. And then, oxygen is 16 and whatever, nitrogen's 14. So it's like, you just go with how big they are. They move slower as they're bigger. So the diffusion and mobility is sort of directly related to the size of the thing.
And interestingly enough, I'm looking, it looks like lithium ion is like 600 picometers. I think they're giving radii here, so you just multiply by 2 if you want the diameter. Zinc 2+ is 74 picometers.
Smaller?
Yeah, so it's smaller. And then a aluminum 3+ ion is 53 picometers. This is all ionic radii, according to the internet. So
well, it's on the internet. It has to be
on the internet. That's just what I looked up. But so yeah, hopefully that answers your question. Yeah, that's a good question. Okay, so there are actually 2 questions from Vinette, who I don't know if we'll be able to kind of answer, because his question is how to set the current range in the Nova software for better current response during electrocatalysis. And then follow up, how to set the upper limit and lower limit current in Nova software during electrocatalysis experiment. What factors decide this range? So we don't use Nova software. You'd have to talk to Metro, I guess, is the company that uses Nova software. But the electrode range, generally speaking, actually, I should pull up. We have a small article on the electrode range that I can use to kind of showcase this electrode range. All right, so I'm going to share this website and no Chrome tab. Okay, so this is electrode range on the Pine Research website, and it actually talks about what it is in a little bit more like these. This will show you where it is on Pine Research. I know it's different in Nova software, but if you're, with whatever technique you're doing, there's the ability to change the electrode range. And actually, as I think about this page needs a little bit more work to describe it in the context of potentiostat operation. But generally speaking, every electrode range, so in this case, I have a plus minus 1 amp range. We use digital to analog and analog to digital converters. All potentiostats should be using these to take what you write and type on your computer and convert it into an analog signal or an analog circuit in your that your potentiostat is using. So what happens is if you have a 16-bit analog to digital converter, that's 2 to the 16 different kind of levels, or I can almost think of them as memory, where a current value is assigned to them, and that determines the range. So for a plus minus 1 amp range, it's a span of 2 amps. If you divide that by 2 to the 16 minus 1 for a degree of freedom, you end up getting a step of 30.5 microamps, which defines the highest resolution that you can measure with this particular current range. And so if you're, what you want to ideally do is in a cyclic voltammogram, I'm here on the 200 microamp range, and this is good. I'm able to kind of see everything. This is actually just some children's Tylenol, acetaminophen in solution, and I'm getting like, peak currents close to 40, 38, microamps of current on the anodic, and then maybe like minus 20 microamps on the cathodic. Now, if I pick a range that's too small, you will cut the your voltammogram. You'll get a duck with a head that's cut off, and you'll just get a flat line.
That's just a crime.
At the range.
I know. What did the duck do to you?
I don't know, but I'll tell you, Peking duck is very delicious. So sometimes it is super good. But you want to pick a range that's not going to overload your potentiostat. And I think on Metrum software, they'll even give you an overload error. So you're passing more current than what the potentiostat can handle, and it limits only 10 microamps of current that will only pass, even though we know that you can take close to 40 microamps. So you don't want this. Similarly, when you start to pick larger ranges, this is the 5 milliamp range, the data becomes noisier. It still contains all the data, but it's clearly noisier. And of course, if you pick a very large range like 100 milliamps, you're looking at lots of digital noise, even though the signal is still there. You can see the anodic and the cathodic waves, but clearly there's a lot of digital noise. So you need to pick the range that is you need to pick the current range where it's the lowest, such that the signal that you measure doesn't get clipped off. So it's very annoying, like if you have a 200 microamp range and your peak current is 201 or 205 microamps, and it's like, oh gosh, you must go to the next range up, even if it's just a little bit more. Or the only other thing you can do is make an adjustment to your electrochemical settings to lower the current. So if you were doing CV, you could say decrease the scan rate to get the current a little bit lower, and that way you could use one range kind of consistently. But that is kind of the nature of current range. How you do it in Nova software, we can't tell you, but the selection of it, of the correct range to use, that's something that I just taught you. So hopefully, Vinette, that was helpful. If you have other questions, please let us know. Okay.
So Antonio has a question next about square wave voltammetry. I have some materials on square wave I can share with you. So for square wave voltammetry of ferrocyanide, although this question probably can be somewhat general to any process, how do you choose the amplitude, step, and range to get the highest, sharpest peak? It's a good question. Let me try to share. So I actually have some slides already on square wave voltammetry. I'll just sort of go through them quickly. Also as a means to sort of, I don't know, walk anybody through, for instance, who isn't sure what square wave voltammetry is. It's kind of a sweep technique, but it's also a pulse technique. And so it is a technique where you are doing basically what you're seeing in front of you here. You're going up and then down in potential at different pulses. Okay. And rather than just sweeping directly from one point to the next. So it's called square wave because, well, you can see that it's rectangular or square in shape effectively. The parameters that are relevant here are the amplitude. Okay, so that's how far from whatever baseline you start, you go up and then down from that baseline. So if I have a 20 millivolt amplitude, I go up 20, then down 40, right? Just to be clear here. So it's kind of like a sine wave thing. You can think about it that way, but it's obviously not sinusoidal. It's a DC method. Well, I guess it's AC. Anyway, I don't want to go down that road. Sorry, not to muddy up the waters here. The next is called the period. So that's how long it takes to do one up positive and then one negative pulse. So for example, this is 33 milliseconds. The increment is how far so I go up 20 and then down 40. And then it's like increment by some amount up 40. Basically, the baseline goes up 8. So as you can think about it as up 20 from this baseline plus the increment and then down 40. Okay, hopefully that's clear. That's how much you're moving the whole thing up each period. And then the sampling width is, for instance, while I'm going up 20, down 40, then up 48, down 20, whatever the numbers happen to be. What I'm actually doing is only taking a point at each of these dots. So you see this red dot. Try to circle it here for you for a second. So I'm only taking a point here and a point here and a point here and a point here. This is actually technically a differential technique. And so what I'm doing is I'm actually taking, like, this is 0.1, 2, let's just say 0.3, 0.4, 0.5, and 0.6. So what I'm actually getting is 1 minus 2, and then 3 minus 4, 5 minus 6. So it's a subtractive technique. So you're going up and then you're subtracting like a baseline. So what this allows you to do is we talked about background current earlier. So basically this is a technique that kind of eliminates background current, background charging. I don't know what you'd say, a comparable CV, for instance, that would have a plot, something like, we have a peak and we have this sort of baseline up here. The comparable square wave might be something like, where the baseline would remain flat because it's subtracting the background current at all times, something of that, like that. Now, the question of how to get the peak really high, I think that the way I would answer that, the problem is to a certain degree, the answer is trial and error. A lot of these, like how far your amplitude goes down will depend on, like, the sharpness of the peak you get is going to depend on the amplitude to a certain degree. Because, for instance, for instance, if you think about a CV, right, here's my CV peak or whatever. So like with a CV, the height of this peak is sort of directly related to the scan rate. Okay. And so I'll talk in a second about the equivalent scan rate for a square wave experiment. So to some degree, the answer of how do I get the peak really high or something like that is faster scan rate. And with square wave, it's a couple of parameters you adjust to effectively get a higher scan rate. You'll get a higher peak. But it also has to do with the background subtractance. So it's like the increment is like taking this point minus this point, and then like this point minus this point. Well, if my amplitude is really big, it's like taking this point minus this point. So it's like this is a bigger subtractive kind of a thing than this, right? So you can just see, without getting too specific, more specific, I guess, if your amplitude is really big, you might get like a larger spread or whatever over some potential combos. But the problem with having an amplitude be like this large is that, like, what happens when you're subtracting this and this? Like, you're missing the peak entirely. So like, does that make any sense? It's usually why the amplitude is somewhat small, because you're trying to capture so you're trying to get like the background you're trying to slice this up into a lot of pieces instead of like, you're not trying to like do like, well, let's slice up the CV into like 4 pieces. It's like, well, that's not really subtracting the background current. Now you're subtracting like pre-oxidized current from post, it's like it's too far, right? In other words, so there is some trial and error, but in general, the amplitude should remain probably relatively small for the square wave to make sense for what you're actually trying to do. Now, this is just 1 over the period is the frequency. So this is where it's sort of like you can talk about it in terms of a frequency. But what I wanted to talk about was the effective scan rate, right? So the increment divided by the period is the effective scan rate of a square wave. So how long it takes to do to do the first set of pulses, 33 milliseconds, for instance, and it moves up 8 millivolts each time you do that. So millivolts per second or milliseconds, whatever, but that's scan rate, right? So it's increment divided by period. So for instance, of the example that I show here, increment of 8 millivolts divided by 33 milliseconds gives you effectively 240 millivolts per second. Okay. And I think we have, for instance, Alex helped do a lot of cool things. This is the Randall-Sevchik equation. There you go. So this is for CV. This isn't exactly analogous or perfectly comparable to square wave, but for instance, with a CV, the peak current that you get is basically proportionate to the scan rate, the square root of the scan rate. Okay, so as the scan rate gets higher, the peak current gets higher. So you can sort of think about it in a similar way, which is to say, if I want to make the peak higher or sharper, okay, I can increase the increment or decrease the period. That will effectively increase the scan rate, and I might get a higher, sharper peak. There's probably diminishing returns to a certain extent. Like I said, if you increment too high, too large, you're taking weight. The slices that I showed you are too far apart. It might not capture the peak all that well. You might like almost increment past the feature you're trying to study. So there's probably some trial and error where you want to go like, if you're trying to like make a really fast scan rate or something like that, you can like increase the increment to a certain extent, but not, don't go too high or whatever. Similar to the period, you can decrease the period. But if your period is so short, the measurement might be really noisy because it's like up, down, up, down, up, so fast that the potentiostat can't measure it properly. Beyond a certain point, it's like, can your potentiostat get you measurement every 100 milliseconds? Fine. Every 30 milliseconds? Probably fine. Every 1 millisecond? Probably. Every 100 microsecond? Well, you're starting to get really fast for the instrument. So at some point, it might not, I don't know, easily be able to measure that. But something in that range, right? Adjusting those parameters with some trial and error. Again, sort of an effective scan rate. You're trying to increase that scan rate, probably sharpens that peak for you a little bit. But again, I would just sort of tell you to exercise some caution, because at some point your parameters might be so kind of out of normal range that the features you're trying to study are not getting studied properly anymore for the square wave technique. So I hope that kind of answers that question for you.
All right. We have a we have a question from LinkedIn, from John. Thank you for waiting, John. We are doing potentiometry with
single wall carbon nanotube.
Single wall carbon nanotubes with an ion-selective membrane. When doing EIS, we essentially never see the classic 45-degree Warburg slope. I've started modeling the Warburg element as a CPE. The exponent is generally closer to 0.3 than 0.45. How do I interpret this? Is this something about the ion-selective electrodes or something I'm possibly doing wrong? And just a PS that he's relatively new to electrochemistry.
It's probably not something you're doing wrong. It's not uncommon to have alpha values of a CPE that are under 0.5. In a similar way that if, for example, you have a semicircle and your alpha value is 0.8, we sort of reason that to be non-ideal capacitance. In a similar way, I would argue something like non-ideal diffusion, or I don't know what the right wording for this is. Like if you're publishing a paper or you're trying to discuss this in an intelligible way, like something is, the diffusion is impacted in some way by something. Now, because you're using a single walled carbon nanotube, I suspect it's possible that you have something where a different model could be appropriate, like a transmission line. This is a situation where you have pores, possibly. Again, I'm making an assumption based on the fact that you're using carbon nanotubes. But when you have an electrode that consists of like a substrate, it's probably a single walled carbon nanotube on something, I would guess, some backing or something of that nature. But it's a nanotube. It's a tube, so it's a pore. There's some tortuous path or something like that, right? The diffusion is probably not just going on a semi-infinite plane away. You might also have diffusion in a pore, or in a microstructure, and the microstructure of your nanotubes might not be perfectly linear. It might not be perfectly. The morphology might be kind of asymmetrical or heterogeneous sort of shape of the surface. All of these things might lead to what I just mentioned, which is to say, okay, well, I don't have 0.5, so I don't have a perfect infinite plane Warburg diffusion, but I might have some confounding or coincidental diffusion of like pore in the pores or something like that, right? Along with, the diffusion layer, like normal Warburg, if you will. And so the aggregate response of my impedance spectrum is that I get 0.3 or 0.4, right? That's the result that I get, because at the lower frequencies, you're just studying sort of most of the time, like all of the diffusion. Now, if the diffusion is happening in sort of like I said, a heterogeneous and asymmetrical way, or there's multiple contributions to that diffusion based on your electrode morphology, you might get something like this. It's one of the benefits of using a CPE, because the alpha value allows you to capture this non-ideality through the alpha parameter. The downside is that what in the world does that actually mean, right? That's the detractors of CPEs, for example, will say, well, this alpha value is just made up. It doesn't, it doesn't relate to reality. And there's truth to that, right? Because what does 0.3 really mean? Well, it's something like I just described, but what exactly does that mean? It's not clear. Like I said, you can consider transmission line element fitting. Sometimes that can help capture this kind of situation, because a transmission line is sort of fundamentally descriptive of a porous electrode where there's heterogeneity in the surface charge throughout the pore. That's what a transmission line is designed to capture. There's variations of different transmission lines, and so you have to find the right one. I'll plug my company's software, for instance. We have a very nice circuit fitting. Where the heck is software? It is somewhere. It's right there. we have a transmission line circuit simulator and circuit fitting element that allows you to adjust all of these elements in the transmission line to fit your specific system based on the boundary conditions, whether there's added inductance or resistance and all this kind of stuff. So sometimes this model can be used, again, as I said, to help fit your specific situation. And you might be able to get a model that kind of looks, I'm just tinkering here for a moment, but I think if we do that, something like this. So for instance, you might be able to kind of fit your model with something like this. Where's my resistor? Maybe you have something like of this going on and it's a little bit of this line. This transmission line model might help sort of fit that. I'm just guessing here. This might not be the perfect model, but hopefully you get the point, right? That might be what you're looking at. And, in short, I mean, impedance is hard, right? In general, but based on what you've written here, I don't suspect you're sort of quote unquote doing anything wrong. This is not an unusual thing. But the last thing I'll mention, as with all data, is run Kramer's Kronig transform on your data, because that would actually be one answer to not necessarily are you doing it wrong, but is there something fundamentally inaccurate about your data to begin with, so that is this 0.3 alpha, 0.4 alpha, is that a real phenomenon that's something like what I just described? Or is it just drift? It's not like I need to adjust my impedance parameters and try again because the data doesn't fit at all. So run Kramer's Kronig and make sure that it fits the low frequency data to begin with, is my first suggestion as well.
All right, very good. We have a follow-up question.
Mm-hmm.
So I run the EIS at OCP to get the RCT for my electrodes. What information can I get if I run the EIS at a potential bias in the faradaic region, maybe at a peak oxidation potential? So I feel like this may be one of Neil's next trigger
you should
issues.
You should answer this one.
So generally speaking, so RCT is the charge transfer resistance. And the charge transfer resistance, when you're at OCP, we're assuming that nothing is happening. Well, nothing's happening because there's no current at the open circuit. So when you run EIS at your open circuit potential, there is a charge transfer resistance, but it might not tell you very much. You actually would find that if you were to actually do EIS at multiple different potentials, you'll get different charge transfer resistances. That's kind of one of the interesting, somewhat amazing things about electrochemistry and some of this redox chemistry, is the fact that the redox reaction actually acts as a variable potential resistor, or a variable resistance, depending on what potential you are. When you're at the potential of the redox reaction or slightly beyond it, it acts as it has a very low charge transfer resistance. It's very easy for current to pass through that molecule. But if you're not at that potential, it's going to represent a very, very large number. So, so what you'll find is that, yeah, you have a really large charge transfer resistance if you went to more negative potentials. Let's say it's you have some kind of oxidation reaction. And if you go in the opposite direction, if you do it at negative potentials, your charge transfer resistance may actually stay the same. It's not actually changing. It's just super, super large. So all that being said, it actually makes sense to do EIS at the faradaic potential. You want your system to be stable, linear and causal. So you need to make sure that your system is stable, but at that potential, you let the system run for a while, and then you run EIS at the potential where the peak, that's the E naught of your reaction. I think you'll actually get perhaps a better value for the charge transfer resistance than the value at open circuit potential. I mean, you're modeling, you're taking EIS under those conditions of the system. So when it's at open circuit potential, I'm willing to actually say it's as if you didn't have the molecule there. And that's what you're taking EIS of. But then when you add the molecule and it's at the potential where something is happening, then you actually get more information about the system. So, yeah, I would, first off, it's a great experiment to actually do. And you may not be getting accurate RCT values if you're doing EIS at OCP for your molecule. So I think that's generally speaking it. I don't think there's any additional stuff. You may actually find if you go past the E naught, which is a good thing, you'll actually get a little bit more information. But I think a lot of people do EIS at multiple potentials, and they look at how the RCT changes over time, or at each potential. So, and that's a very kind of indicative thing of what's going on in their system.
You've saved me from having to answer this in my usual aggravated manner. So thank you.
Yes.
We have been saved.
All right. Next question is from Antonio. And of course, if you've asked questions on LinkedIn and if you've put questions in the chat for either Twitter or YouTube, we are getting to them. We do want to provide thorough answers to all of your questions. Antonio asked, can we monitor layer by layer sensor assembly on a screen printed electrode using non-faradaic EIS in KCl, tracking resistance from bare to antibody-modified?
Yes.
Yeah.
Let me show you an example of that exact
thing. You have an example of that.
If you remember, I'm talking to you, maybe everybody here, but
yeah.
if you are in the audience and you do remember, that's impressive. I did a webinar on this maybe 3 years ago. So, for instance, this was a person who submitted their data to me asking about some strange behavior. I won't get into necessarily all of the details of it, but what you are asking about is what this person did specifically, which is that they took a screen printed electrode, sort of a naked carbon screen printed electrode, and then they did this process. You can just see the process in front of you here. This isn't my data, so I can't speak fully to exactly what it is, but they used hydrochloric acid and sodium nitrite, grafted this PABA, poly something B something, and then they grafted a carboxylic NHS something on it and activated it, and then they did it at pH 5 and did another special graft, and then they put this bovine serum albumin, and effectively this was used it's a disease biomarker detector, right? I mean, this is why you modify electrodes or whatever. What they did basically was impedance at each step. And so your question related to non-faradaic is somewhat specific. I'm pulling up our software. I have their data right here. I'm just going to step through this here for you. Whether it's faradaic or non-faradaic, I don't have any particular speaking to. Probably you can do either. It depends on what you're trying to study, I guess. If you're trying to study just sort of how the resistance sort of, I don't know, IR resistance is changing, then you might do non-faradaic. If you're trying to study the process or the sensing, you would pick a faradaic potential. So whether it's non-faradaic or faradaic, excuse me, they got, for example, this, Nyquist Bode plot result on the plain carbon SPE after they grafted the PABA, whatever in the world that is. I'm not a polymer expert. It's not my data either, as I clarify here. The data changed slightly, right? When they grafted this carboxylic something onto it, they got much different results, some more semicircles. And what they were specifically interested in this particular webinar, which I covered, was once they started grafting this activated material, and the serum albumin, they got this very fun, now I'm going to trigger Alex, behavior here where they got this little curl, kind of funny looking curl at high frequency. So they got this kind of inductive loop behavior. I'm actually not going to talk about that, not the least of which I want Alex to still talk to me later. But the point of this is not necessarily to analyze each of these, but to say that what they did is exactly what you're asking. And so, yeah, for sure, one of the real benefits of impedance, for instance, is that you can, have this multi-step layer by layer assembly. And as long as your electrode between each layer, between each step, between each process is still like intact, you can run a quick impedance experiment on it and check the response and see how the resistance changes. Heck, you can see how the capacitance changes, how the diffusional behavior is changing. The OCP might shift. Like all sorts of things are going to happen when you modify the electrode. So so that's just one example for you, but absolutely, this is something that you can do.
All right, the next question, which Neil may be a little more capable of answering it than me, is from Nibbles 360. How do I choose the excitation current amplitude for galvanostatic EIS?
Yeah.
As opposed to, say, potentiostatic potential.
With galvanostatic EIS, you have to be careful. It has a higher probability of being dangerous than potentiostatic impedance. So one of the things I just said like 20 minutes ago was, don't worry about impedance. It's not invasive. So you can do all these different amplitudes, and it's a great way to not damage your samples. That goes out the window once you start doing galvanostatic impedance if you're not careful. Because if you pick too high of an amplitude for your galvanostatic impedance experiment, you could swing the potential very, very high. So as an example, if you're studying batteries, which is what galvanostatic impedance is used most commonly for, right? If it's something else, this is not exactly the right, it's not perfectly analogous, but for example, with batteries, you could start at something like C over 100. So for instance, if you have a 100 milliamp hour battery, like that's the capacity of your battery, whether it's a coin cell or a cylindrical cell, anything, right? You could start with 1 milliamp amplitude. That's C over 100. So 1/100th of the capacity, that amplitude could be a starting point. Most probably that won't be enough to get you good data, but that's okay. So in general, that's a metric that you can try for a battery. If it's not a battery, my advice is, generally speaking, start with something very small. Probably not nanoamps, like most things won't respond at all to a nanoamp, but again, it depends on the size of your electrodes, what system you're studying, how big it is, how much current it like gives you in a normal experiment, for example. But a small percentage of the normal amount of current you would measure in a normal experiment is where you should begin. If the data looks terrible, slowly increase the amplitude until you get a reasonable signal. Because remember, impedance requires linearity, causality, and stability. As you increase the amplitude, you will start to get data that looks real, because if it's too small, it's just not responding. It's not enough to impede the system. And that's okay. Bad data from too small an amplitude is okay, because you're not damaging anything. Again, it's another one of the things, like the benefits of impedance. Whatever frequency range you pick at a very small amplitude is not going to damage your system. Your data will be garbage, but that's okay. That's like a starting point. Okay, so it was too noisy. My data looks bad. All right, no problem. Let's double the amplitude. Try again. Oh, it's still noisy. All right, let's add another. Let's 2x it again. Whatever. Like slowly increase the amplitude until the data start to look good. Or clean, smooth, whatever. You should be able to sort of find that place. Roughly speaking, the minimum amplitude at which you get good-looking data, but it's not too high that you're not linear, you're not stable, basically. But you should be very cautious with galvanostatic in general to start somewhere small, because that is a situation where too large of an amplitude, you could damage your system.
Haven't you mentioned also that, like, if you have an idea that your system has about like 1 kilo ohm of resistance. Well, if you put 1 milliamp in, you're going to get like a volt swing.
Yeah. You can use Ohm's law for that too. Yeah.
To get like an approximation of where to start.
That's a good point. I'll bring that up really quick because that is a good point.
And potentiostats can measure millivolts and volts pretty well. When you get to microvolts, you're hitting the limit of what the potentiostat can really accurately measure. But
yeah, so let me pull up.
While Neil pulls that up, I will mention that we do see a lot of questions coming in. We will get to them. So don't worry. We will answer your questions as they come in.
Okay. So to that point, Alex mentioned, I'll just go through this really quickly. So yeah, so think about Ohm's law when it comes to the amplitude, right? Z or Ohm's law of E equals IZ, V equals IR. This is the same thing, right? Basically, if your impedance of your system is 1 kilo ohm, for instance, a 10 millivolt amplitude means 10 microamps, right? Or alternatively, as a galvanostatic situation, if I choose 10 microamps over 1 kilo ohm, I'm going to get 10 millivolts of potential up and down. So either direction, I suppose you could think about it that way. So that was all I wanted to show you, was basically just Ohm's law, right? So like the other situation here, like a really, really small, if your impedance is really small, this is like 10 millivolts gives you 10 amps. This is like the opposite, like talking about potentiostatic mode. The point being, you can do Ohm's law and, for instance, say, okay, well, if I have 1 milliamp here, I'm going to get, microvolt, and it's too low. So you can just do a quick Ohm's law kind of estimate, if roughly speaking what the impedance of your system is, to estimate where it could start. And it might be a similar thing to what I said, where it's like 1/100th of the amount of current might end up working about to be the same estimate, but something along those lines will probably help you start.
Yeah. All right. We have a couple questions from I think this is Qingdao, Rin's car wash company. He wants to know how to determine the resistance value after running EAIS. Specifically, he's looking at the resistance. He asked for a ferrocyanide in potassium chloride solution. He's using a CHI 660 workstation. And he also has kind of a follow-up question that came a bit later, but while we're talking about him, he's also asking about the parameters for chronocoulometry, especially for this ferrocyanide solution. And he's asking the question that we answered in the beginning of the live stream, the first question, which was how to calculate the effective surface area after running chronocoulometry.
So we won't answer that again because I answered.
Yeah,
I talked about chronocoulometry, and I talked about the electrochemically active surface area, specifically showing how to calculate it for a platinum hydrogen couple, not specifically for the ferrocyanide. I talked about why that's not exactly easy or the same sort of thing. So Qingdao, if you want to review that, you seem to be on YouTube. Basically, you can just rewind this live stream to the very beginning. It was the first. Was it the first one I answered? I think it was the
first question that you answered.
So the beginning of this live stream, I answered that question. So we won't talk about that again. The last part, and then the first part. Determining the resistance. First of all, it depends on what resistance you're asking about, and then if you're specifically asking about how to do it in the CH Instruments software, I can't help you. I don't. We're Pine, right? So I can't really assist you with another company's software too well. Of course, it's just not my company's instrument, right? But in short, the resistance, if you're talking about like the ohmic resistance,
for like a ferrocyanide and KCl solution, we'll just assume that's it for now.
For instance, if you're talking about that, if you're looking at a Nyquist plot, for instance, and let's say you're studying around the, so that this is Z real, this is minus Z imaginary, this is the origin. If you're studying the ferricyanide and you have maybe, you know, a Nyquist plot like this, for instance, this distance right here, that would be your like ohmic resistance, and then the width of this semicircle right here is the charge transfer resistance. So these are just sort of basic fundamentals. I've given a webinar about this, I think last week or the week before, whenever it was specifically, where I worked out this mathematically and showed where these come from. But so you didn't specify which resistance specifically you're asking about, but if you have Nyquist plot or impedance data that looks something like this, these are where the resistors, for instance, if your circuit is something very standard like a Randall's circuit, this is the, for example, ohmic resistance, double layer capacitance, and this is your charge transfer resistance down here. So that's where you can extrapolate those numbers. Basically, you could do a circuit fit, or you could just eyeball them from your Nyquist plot. That's where they come from.
And I would imagine CH Instruments should be providing you with Nyquist and Bode plots.
Yeah, and I don't know about their circuit fitting.
We don't know.
I don't know what they have precisely, to be honest. But if they don't, you could use another program. Our circuit fitting, for instance, is also available. We sell, or you could use another program to do circuit fitting and do some sort of analyses in a auxiliary, you know, graphing program or what have you. So that's sort of the long and short of resistance, I suppose, in EIS data.
Yeah. There's a question from a True Channel. I don't think we're going to be able to answer this because the Born-Haber cycle, I don't think actually has much to do with electrochemistry. And we don't actually, unless you know a lot about the Born-Haber cycle.
Something about lattice energy.
Huh?
Something about lattice energy. I don't know.
Oh, lattice energy? Oh, I thought it was a catalytic experiment.
Born-Haber cycle is it requires, let's see. It's an enthalpy. Born-Haber cycle is
it's an approach to analyze reaction energies.
Yeah, determine the lattice energy of an ionic solid, ionization energy, electron affinity, dissociation energy. Yeah, I don't know that this is electrochemical, although it might have some. I'm not sure if there's redox involved, but it's mostly, I think it's like dissociation of ions.
Yeah,
I can't speak more to it.
Yeah,
I don't know. Lattice energy. I mean, it's more of a chemistry / thermodynamics kind of phenomenon, and I can't speak more to it. So I think we're going to have to skip this, unfortunately.
Yeah,
I don't know.
Yeah, sorry.
I don't know that I can cover this and give it the justice that it's due. You know what I mean?
Yeah.
So apologies, True Channel. It's a little beyond our expertise and perhaps a little beyond electrochemistry as a discipline.
Yeah. Let's see, going through because we don't have too much time.
I'll try to get through everything.
Yeah. In CV experiment using drop casting technique on a glassy carbon electrode, is there absorption control or diffusion control most probably happened? Drop casting technique.
I don't know what absorption control is. Not sure what you mean by that.
Yeah, like, so if you're when you drop cast so usually if you have something on the surface of your electrode, and that's the thing doing the chemistry, usually it is the molecule that's dissolved in solution that is responsible for doing the electrochemistry, sort of say. It's like you're doing the electrochemistry of that. Adsorption control, I'm assuming, is the electron transfer is just happening to the molecules that are adsorbed on the surface. If it's diffusion controlled, and when we say control, it's like it's the limit. It's like that's the thing that limits how much current. Like in a stationary CV experiment, diffusion limits the current response. It's a diffusion controlled process. But if you have if you're in an RDE experiment, rotating disk, it's convection. It's like a combination of convection and diffusion controlled. Now, if it's absorption controlled, it just means it's not diffusion controlled. It's just on the surface. The molecules are just stuck on the surface, and they're not coming. They're not like coming into the electrode. They're not moving around. They're just on the surface, and they either gain an electron and lose an electron. And so, if you have a system that is purely absorption controlled, you should get like a very sharp spike in the current. It won't be kind of a long kind of like wave that you would see in a traditional CV. It would be like a very sharp spike that's associated with just like electrons were transferred, and then when you oxidize them, they go the opposite direction, and they usually don't have a 57 millivolt peak splitting between the cathodic and the anodic wave. That's how you know it's an absorption controlled or surface bound electrochemical process. Diffusion is when you have that nice kind of wave with 57 millivolt peak splitting between them. So I hope that kind of answers the question. But the drop casting technique, I think, is just to put something on the surface. So unless we knew more about what the drop casting technique was, or what you're using with it, like, are you drop casting something on and then doing electrochemistry to generate something on your glassy carbon electrode, and that's like your catalyst, and that's, you want to know if that's absorption or diffusion controlled. Let us know if that's, if you give us a little more clarity, we can probably help with that. All right, moving on. The next question is why there is a minus symbol in, I think it's supposed to be front of imaginary impedance.
Yeah, it's just mathematics.
Yeah,
I'll show you. So the mathematics of the imaginary impedance. So real impedance, the expression is Z real is equal to the magnitude of the impedance times the cosine of the phase angle, and Z imaginary is equal to Z mag sine of phi or phi, whatever. The only reason why we do this is because Zi is almost always a negative number. That's it. So if we look at, this is probably something that you hopefully learned, I don't know, in high school maybe. If we look at sine cosines in all four quadrants, right? In the first quadrant here, sine and cosine are both positive numbers. But in the fourth quadrant, it's the fourth quadrant down here, cosine's positive, but sine is negative. This is where most of our phase angles end up. They end up down here. Okay. So this is simply a matter of mathematics. For a angle that is in the fourth quadrant, my cosine is positive and my sine is negative. So all that means is that when I do the mathematics, my Z real ends up being positive most of the time, and my Zi ends up being negative most of the time. It's literally just trigonometry that causes this to be the case. And so what we do is we plot minus Zi so that these Nyquist plots look this way. There's literally no other reason, because all that would happen if we didn't is that we would get that and that and that and that. Get rid of these things. It's literally the only reason, because our brains see this and it looks upside down. That's it. That's the only reason. It's convenient to look at semicircles right side up, if you will, and so we plot minus Zi, so things look right and the world is all nice and happy. That's it. It's just mathematics. So
very, very good. Let's see. JD Physics has something. I think we probably need a little more information, but JD is asking, can you help me to EIS using electrolytic solution? Which electrolyte or electrolytic solution is better for EIS parameters?
I'm not sure there's an answer to that question.
Yeah. It depends what you want to do. EIS is a technique to help you learn more about your particular electrochemical system. So you don't need to change your system so that you have better EIS. Well, I mean, no, you might want to change your system around to get better EIS data, but you don't need to just get like, if you want to get the best EIS data, use circuits, use like a capacitor and a resistor and all those things. You'll get really, really good impedance data. But there is no kind of great electrolyte solution for EIS.
I mean, I guess you could say something like, if your electrolyte has a higher concentration of analyte, or supporting electrolyte, the resistance will be lower. And maybe if you're studying whatever you're studying, there will be less interference or impedance from the electrolyte itself. So like if you're studying 0.0001 molar, whatever, right? You're going to have like a really high impedance, and maybe it will make it hard to measure like the charge transfer resistance, because the impedance of the electrolyte is so high and it's just, it's messy or something.
Yeah.
Whereas if you do like 0.5 molar, you'll get better resolution. So in some ways you could say something like that. But I mean, if you're talking about like, oh, what's better, like KCl or sulfuric acid or KOH or perchloric acid, like which should you, it's like, there isn't really an answer from the perspective of impedance very easily, because why you would use one solvent compared to another, or one electrolyte compared to another, is more related to your specific electrochemistry, your electrodes, the stability of your working and your reference and your counter electrodes, and what reaction you're trying to study. It's way more dependent on those things than it is on the impedance experiment, right? You can do impedance in any of those electrolytes, but you might not be able to use sulfuric acid with this particular electrode for one reason, and you have to use hydrochloric acid instead for whatever reason, right? The impedance isn't the reason why you would pick one of those over the other. So I hope that's a little bit clear as far as that is concerned. And then let's see here. Thado had asked a question: what technique would you use to study degradation mechanisms on electrodes and catalysts for water electrolysis? Impedance. It's not so much a question of, I mean, almost anything is probably going to be used. I mean, water electrolysis, if you're studying oxygen evolution reaction or the hydrogen evolution reaction, which are the extremes of water electrolysis, the electrochemistry you're studying there is going to be typically a sweep. I talked about this an hour ago in this same live stream, so you can probably back up. If you're watching this on YouTube at a later time, the timestamps are probably in the description. You can find where I answered the question earlier about OER and HER and overpotential, for instance. And so one of the metrics, for instance, of your electrode and your catalyst studying water electrolysis, like OER and HER specifically, is the overpotential. And so one kind of answer you could have, for instance, to study the degradation of your electrode would be something like, how does the overpotential change with time for the same electrode, right? Okay, well, I do OER, 1,000 cycles over 2 weeks or something. I'm just making up numbers here, right? But it's like, okay, well, the overpotential was only like 50 millivolts in the beginning, and then by the end of 1,000 cycles, it didn't, the overpotential increased to 200 millivolts. So there's some degradation because the overpotential is worse. Some like that's one metric. So that's like a sweep technique. Impedance you could use, for instance, to measure like the charge transfer resistance. Pick a faradaic potential of the oxygen evolution or the hydrogen evolution reaction. Pick a potential where that's occurring, and measure the impedance of your electrode on your electrode of the OER, of the HER, whatever. You'll get like maybe a semicircle, maybe some diffusion, maybe whatever. You'll measure some resistances, for instance, and you can measure over time, if the resistance starts to increase, it could indicate degradation. It could indicate a lack of catalytic activity. So those are some of the ways that you could do that. But in some sense, almost any electrochemical experiment that you're doing whether it's EIS or like CV or linear sweep. You're studying how it goes over time, over repeated, tests, and that is a way to check how well your electrode is performing the water electrolysis. And then in extension of that, is it degrading, right? The actual degradation might take the form of like the electrochemical experiments coupled with like microscopy. Like maybe you might, take an image of it afterwards and see, did it actually like fall apart or something like that. But those are some of the electrochemical studies that you might be able to use to look at degradation.
Yeah. Using other techniques, images and stuff is also helpful.
Yeah, like spectroscopy could probably help a lot.
Yeah. So we have, let's see, another question. Please tell me the reason for the absence of a semicircle in the Nyquist plot. He's only getting like a quarter of the semicircle to appear. Well, sometimes I've actually seen some issues where you have it.
You can keep talking. I'm just gonna I'm gonna pull up a simulation and kind of show.
Yeah, keep an eye out. Sometimes your semicircle is also very, very small. It's like the main feature may show more of the diffusional type of aspects, but generally sometimes even in one of the first things Neil had earlier, the semicircle was actually very, very small, and then you saw like another semicircle, but it was much, much bigger and only part way there. But also how far you scan, I've just found that the reference electrodes really just cause a lot of problems.
Yeah, that could be one reason. Reference electrode. It could be some experimental thing going on for sure. Could be an error. Run Kramer's Kronig on your impedance data to check that your data is actually good data. Assuming your data is good, the two simplest answers to the question of why do I not have a complete semicircle, one of them is the frequency range, the other is the value of the capacitor or CPE. So you can see here, this is a simple like RC right here. I have a perfect semicircle. One way to get a not complete semicircle is increase the capacitor. So if my capacitance value is large, you see that the semicircle will not complete. So very, very simply, it could just mean that you have a very large capacitance, or you have diffusion, because there's in some sense not much difference between a very large capacitance and semi-infinite diffusion. Whether it's a semicircle or it's a straight line, sometimes that's again related to the accuracy of your data. So run Kramer's Kronig. The other possibility is that you did not go to a low enough frequency. So for instance, if I have mostly a semicircle, but I go to a minimum frequency that's not low enough, let's see if I can get this to cut off, but not totally cut off. There you go. So I only went to 10 hertz for some reason. Now it's not completely finishing. But then I do my experiment again and I go way too low, but it took forever. Now I get my full semicircle. So frequency, if you go to a low enough frequency, the semicircle will complete. That presents its own problems because very, very low frequency can take a long time and you can introduce more error. But in theory, if you go to a low enough frequency and you have a faradaic process, the semicircle will complete. Or it just, again, means that you have a very large capacitor. And because it's a large capacitance, because its impedance is inversely related to frequency, you have to go to a very low frequency to fully charge or discharge that capacitor. And so you don't get a full semicircle. So there you go.
I think this will be the last question I think that we look at is from Love. Love is asking, first I want to ask about the effect of electrolyte concentration on square wave. I've heard before to leave solutions for square wave with less concentration to get better voltammograms. Is this true, or should I keep the same? Should I keep it the same as I would for CV, say around 0.1 to 0.2 molar solutions?
Interesting.
Less
concentration to get a better with square wave.
I don't see why it would.
Well, the only thing that I can think is that, for instance, I'm not sure. There might be a reasoning that I'm not aware of. So for sure, I might be ignorant of like an actual reason for it. But what I would say, for instance, is that square wave might present the opportunity to get decent voltammograms if you have a lower concentration electrolyte, and like you have to for whatever reason, because it is a background subtractive process. If you are stuck with low concentration electrolyte such that CV is really ugly because it's got such a wide band, well, square wave might be a good option because it subtracts that high background.
It's a difference technique.
Exactly. Yeah. But it's like, if you have the option to do like 0.1 molar and you just choose to do 0.001 molar, I don't know that you'll see a benefit. I just think it's more like, again, it's like in a situation where for whatever reason, experimentally, you like have to study at very low concentrations. You might find that square wave is a better technique than cyclic voltammetry because of its subtractive property, if you will. That's my take on it. I can't think of a good reason, which isn't to say there isn't one, but I'm not aware of one, and I can't think of a good reason why you would willingly choose lower electrolyte concentration and it would improve your data compared to higher electrolyte concentration by virtue of doing square wave. I don't know that reason. There might be one, and I'm just not aware of it for sure. But that's the answer I can give you, is that similarly to doing like IR compensation, where you correct a problem that exists and you can get good looking data by like the potentiostat compensates for the IR drop.
Yeah.
Right. It's not that there isn't an IR drop, but you have a bad IR drop, you can correct for it. Okay, fine. So it's like same thing. You have a low electrolyte concentration, you have a high, background current. Well, square wave can kind of correct for that because you can still get a fairly resolved peak because it's a subtractive. So the background current goes away even if it's large.
Yeah.
That's my guess. Unless there might be something else, again, just to full disclosure. Like, I don't know. I might not know something about this specifically, but that's what I can tell you.
Yeah. I mean, I can't see any reason. Not that I know very much, but like why it would be better to have a low electrolyte concentration. I don't think so. So I would say keep it the same, especially if you're comparing your results from one experiment to the next. You'll have the same concentration of electrolyte between CV and square wave. But
then they'll be comparable at the very least.
Right? Yeah, they'll be comparable. Well, we're kind of out of time, but Isaac Frazier is just asking, what is the scheduling for these sessions? We always try our best to meet on Fridays, Eastern Standard Time at 1 p.m.
U.S.
Eastern Standard Time at 1 p.m. We usually do this for about 2 hours every week. Sometimes there are weeks where both Neil and I are out traveling because of work. But generally speaking, we try to do these sessions every week, every Friday. So, and if you're unable to make it, you can still type in your question. And, we answered about 3 questions before, or earlier before we started getting some. So ask your questions ahead of time if you can't make it. But we'd love to have you listen in on the live stream.
Yeah, it's great to have the questions live. And like I said, like Alex said, we answered a few questions before, because when you ask a question in the comments, you can leave a comment, below the video on YouTube, and we'll answer it on YouTube as well. But when it's a question like the ones that we answered at the beginning of the live stream today, when it's a question that warrants a explanation, that we can draw something or talk live about it, we kick it to the next live stream, so we can do justice to the question. We want to try to answer as thoroughly and, as intelligibly, I guess, as we can. Right. And so that's why we do these sessions. So we really appreciate everybody joining us. And, we keep showing up and you keep asking us questions. And if there are no questions, then we'll find something else to do with our time. But
that's right.
we're very happy to do this. We do appreciate all the engagement and, like I said, thanks, Isaac, and join us every week if you want. And if you have questions, we're happy to keep doing our best to answer them. So I guess with that, I think we're both here next week.
Yes. Yeah.
It's like
I don't have any, I finally don't have any travel until
it's like
Thanksgiving
some kind
time
of record.
frame.
Yeah. I think actually I'm here until Thanksgiving also.
Yeah.
So several weeks. And I have a webinar next Wednesday. Is it next Wednesday? It is next Wednesday.
Yeah.
In fact, I have one over the next 2 weeks. 2 weeks in a row, if you can believe it. The madness. I'm sort of announcing one at a time, so I'm not trying to get too ahead of myself here. But next week, I will be doing a webinar on Wednesday, 2 time slots, and it's on Warburg elements and corrosion models and things like that. And so I hope you'll join me. You can go to pineresearch.com. You can scroll down a little bit. You'll see the webinar registration link. You can register for that. And I'm sending an email about it soon, actually, tonight-ish. So anyway, I hope that those of you who join my webinars keep joining. I appreciate that as well. I like doing webinars. And anyway, for now, I do see there's some questions coming in. We've reached the end of this live stream. We'll try to get to questions next week. I know it's a bit of a pain to have to wait.
I'm already adding it into the
queue
for
Arthur.
Next week.
Sorry, we're literally wrapping everything up at the moment. But we'll try to answer that first thing next week at our live streams. We're at the end of this one. So with that, again, thank you everybody. We appreciate your engagement, questions, and everything. Every Friday around 1 p.m. Eastern time. This is when we do these, and we'll see you next week. Everybody have a good weekend.
Bye.